Hello everyone, welcome back to Math Specs. My name is Stephanie, and today we're going to begin our pre-calculus series by discussing domains of functions. So first, we're going to begin by discussing the definition of what a domain is. And on the slide, we've written that the domain of a function is a set of all possible inputs. And what we mean by possible inputs is our x values. So inputs means our x values. So what would be some very interesting x values that we could sort of test? We're interested in negative numbers. We're interested in 0. And we're also interested in positive numbers. And we want to know if all of these are possible inputs for our functions. And we will see examples of this in the following slides. So for the first example, we're asked to find the domain of this function. And we know that anything that the expressions under the radicals have to be greater than or equal to 0. So to find this domain, we're going to set this expression greater than or equal to 0. So this is what we're going to do, and we are going to solve for x. Okay, so I'm going to subtract 1 from both sides to get x alone on the other side of the inequality. These ones will cancel. Then I will bring down my x, and I'll bring down my inequality. 0 minus -1 will give me -1. So x will be greater than or equal to -1. This will be our domain for this function. So the domain of g will be -1. And we've put this bracket because our inequality is greater than or equal to. So we are including the -1 in our domain, comma, positive infinity, parentheses. Okay. And to the right, you will see our graph. And here we're starting at -1, and we're continuing on to positive infinity in this direction. Okay. So let's go ahead and go on to the next example. Again, we're asked to find the domain of this linear equation. And here it is to the right. This is our equation. This is the graph. H of x is equal to x plus 1, or y is equal to x plus 1. And so we're asked to find the domain of this. So what we're going to do is actually look at all of our possible values. Although my graph only goes up to -6 and +6, this graph will extend in both directions, into both directions, in positive infinity and negative infinity. So our domain is going to be negative infinity to positive infinity. And I've decided this because there's a rule that states that the domain of polynomial functions is all real numbers. And a linear equation is a polynomial function, so we have linear functions. Linear functions, which are y is equal to mx plus b. Also quadratic functions, quadratics, where we have y is equal to x squared, and cubic functions, so y is equal to x cubed, and also the root function y is equal to the cubic root of x. Okay, all of these, their domain will be all real numbers, so it will be negative infinity to positive infinity. Okay. And this is actually really helpful when we don't have graphs to help us, and it's just a good thing to memorize. So I would commit this to memory. Okay. So right, memorize. That'd be so this would be a good thing to memorize and to keep in mind. Okay. So let's go ahead and go on to the next example where we have a cubic function, a cubic root. And from our previous slide, we know that the domain of cubic roots are all real numbers. And you can see on this graph to the right that it extends in both the negative values of the x-axis as well as the positive values. And if you were to actually graph this in a graphing tool such as Desmos, you would actually see this continue on in both directions. So here you would write that the domain of G will be negative infinity to positive infinity, because this cubic root function can actually handle the negative values. So if you were to actually plug in a negative number into here, you would actually, some negative value like -4, this cubic root would actually be able to solve that for you. And I encourage you to plug in a positive number and to see that you get answers for both. Okay, so you would get something like this, like 2 minus 1. Okay, so that would be a good exercise for at home. To kind of prove to yourself that this function can handle negative numbers and positive values, and you can choose whichever negative or positive values that you would like. So here we're asked to find the domain of this rational function, and this would be a really good graph at home exercise. I encourage you to do this. I also encourage you to graph all of the other functions I introduced in this lecture. You can go to desmos.com, and it's a free graphing tool for students and classrooms. And if you've never used it, now would be a really good time to get acquainted with it. It's really fun, and it can be really helpful for understanding what these functions look like in graphical form. And it's also a really good place for you to just practice graphing, because as you advance more in your math academic journey, you will begin to use more graphing tools, and graphs really are extremely helpful in your overall understanding. So go ahead and graph this at home. You should get something, well, it is a rational function, so you'll get something like this. Have one part of the graph like this, and you'll have another part of the graph like this. Okay. And this value that right here, this vertical line, this is a vertical asymptote. So this will be at x is equal to 8. This is your y-axis, and this will be your x-axis. Okay, so your graph should look something like this, but I definitely do encourage you to graph this at home, on the computer and a tablet, or even on a phone. So let's go ahead and find the domain. And first, I would like to ask you when is this undefined? And it will be undefined when our denominator is equal to 0. And if you go ahead and look at this, what value of x would make this denominator equal to 0? When x is equal to 8. So if we were to plug in 8, so we'd write x is equal to 8. When x is equal to 8, this is undefined. So when we plug in 8, we would 5 minus 8 minus 8. 5 minus, and then 5 over, and then 8 minus 8 would give you 0. So then this would be undefined at x is equal to 8. Okay, so in order to find the domain, we would have to find the values where x minus 8, where the denominator is not equal to 0. Okay, so this is how we find the domain. Denominator cannot equal 0. So we solve for x, so then this would be x, so then therefore x cannot equal 8. Okay, because when x equals 8, like up here, we have 8 minus 8 in the denominator, and that's going to give us 0, and you can't divide by 0. Okay, so I'll write that out. So it's undefined because you cannot divide by 0. By 0. Okay, so then this is our domain, but what we're gonna write it as, our domain will be negative infinity to 8, and it's not included. We have to write the parentheses, not the bracket, because we cannot include this in our domain. Union, it's gonna go from 8 to positive infinity. Okay, so then when you graph this at home, you're going to see that. You're going to see that our graph is split into two, and there's going to be this imaginary separation. That is our vertical asymptote of x is equal to 8 that is actually separating both of these graphs. Well, so as you see here, here's negative infinity. These are our negative values for x. So let's it's going to go from negative infinity to 8. So here we are, negative infinity, we're going, and then as we get to 8, we get super close to it, but we don't ever cross this vertical asymptote. And the other part is from positive 8 to positive infinity. So here we are at the top at positive 8. This is x is equal to 8. We don't cross this vertical asymptote. We get super close to it. And then we go on to positive infinity in this direction. It's going to continue to the right. Okay. And of course, when you graph this at home on Desmos, you'll be able to see it in a much better form. Okay. And I always encourage you to draw out your functions. If you know what the graph looks like, make a table. Maybe you can make an XY table and just put in values and see what that graph would look like. But definitely graphing is a very good handy skill that you can develop along your math career as a student. Okay, so let's go ahead and continue. Here we're asked to find the domain of this function. Again, we have a square root, so we know that the expression under the square root has to be greater than or equal to 0. So that's what I'm going to write. So this is how we're going to find the domain. And now we're going to solve for x, basically. Solve for x. So I'm going to move the 4 to the other side by subtracting. So I'm going to write negative x squared greater than or equal to negative 4. I moved the 4 to the other side by subtracting 4 and subtracting 4. Now I'm going to divide the negative numbers, the negative 1. So this will give me x squared. And now I have to flip my inequality. Negative 4 divided by negative 1 is going to give me positive 4. Now I'm going to take care of this power. So I'm going to take the square root, both sides. And now I'll be left with the absolute value of x is less than or equal to 2. Okay, so now I'm going to write this out. So it's going to be x equal to less than or equal to 2 and negative 2. So our domain for this function is going to be negative 2 to positive 2. And both of these values will be included because our inequality is less than or equal to or greater than or equal to. Okay, so that is our domain. And if you were to look at the graph, you'd be able to see that as well. Okay, so let's go ahead and continue. I think that is the last example, and it is. Thank you so much for your time and attention today. Next time, we're going to continue with the difference quotient and and how important it is in calculus. So I hope that you can join me for that. Thank you so much for your time, and until next time.